Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my channel, and in today's video we'll try to understand how to handle the double integral with respect to polar coordinates, because in the previous lectures dealing with the same series of the videos related to the double integrals, we simply endeavored to cover how to evaluate the double integrals by means of the Cartesian coordinates. Now, over here today in this video, we'll try to handle the double integral with respect to the polar coordinates. Okay, in polar coordinates, what exactly the coordinates are? They are the angle, one of it is the angle, and another one is the radial segment, magnitude. Okay, so how we just try to write the Cartesian coordinate? We just write the Cartesian coordinate in terms of abscissa and ordinate x and y, and in polar the coordinates are expressed with respect to the magnitude of the radius and the angle theta. All right, so over here I just tried to manage a figure, though it is not complete, it's just a starting. So this time my plane G, this is the plane G, and it is bounded by the two rays which are having the angle alpha and beta. You can see that this ray originating from this origin, and this time the origin is the pole here, or actually what exactly a pole? A point with respect to which we are managing a certain angle. That point is called a pole. Okay, and the line with respect to which we are managing the angle is called the initial line. So this over here, the x-axis is behaving my initial line, and this point is behaving as my pole. So I just draw a ray like this, having an angle theta equals to alpha, and another ray is this, which is having angle theta equals to beta. Okay, starting from the initial line. We always calculate the angle with respect to the initial line, we know that. So this is it. So this is plane G, is bounded by these two rays having these angles, and also it is bounded by two circles having radius r equals to a and another circle r equals to b. So I have just highlighted here the arcs of these respective circles having the particular and having the subjective radii. So I have just tried to highlight here the arcs with green color. So this G is bounded by these two blue rays and these two green arcs. Okay, that's it. So now I will try to divide this entire plane G by means of several arcs representing several circles bounded by these two major circles are having radii r equals to a and r equals to b. So within these two circles, between these two circles, I will try to manage a couple of more circles, and I just say that let it be n number of circles. So they are going to have, I'm going to have a strips like this. So let me draw those circles now. So that's how it looks like. Okay, so between these two circles, these two big circles highlighted by these arcs, I've just maintained few more circles between them, and let us assume that let it be n number of circles. Okay, n is any natural number, so there are n number of circles. So now you can see that this entire plane G is now divided into several such strips. Okay, curved strips, it's like that. Now furthermore, what I'm going to do is that I will draw two more rays having angles between alpha and beta. Okay, so I will draw two more rays right between these two rays. Okay, so you can also say that the angle of those rays are going to be between these two angles. Okay, so let me just manage those two rays as well. Okay, that's how it looks like. So you can see that these two rays, the angle of, if I talk about this ray, the angle of this ray from initial line up to here, if I call it theta I minus 1, I is any number, it's like that. It's just a general way of representation. And talk about the angle of this ray with respect to this initial line, it's from here to here, and I call it theta I. Okay, and both these angles are between these two, alpha and beta. It lies within this range. So now you see, let me just manage here. Let me just try to highlight a certain segment right over here. So make sure that if your number of circles that we have so drawn between these two major circles, if the number of those circles are tending to infinity, it's like that, then in this way, this curved segment is no more going to be curved. It is going to be in a form of a rectangle, because the smaller is going to be the size of the segment, then more flatter it is going to be. All right, so we just try to open our third eye like that. So I just call it curved subrectangle for my A's, and if I just try to manage here a diagonal, this is the diagonal. The length of the diagonal, I just call it is represented by norm of P, where P is the length of the diagonal. Okay, so you see, once when n approaches to 0 and approaches to infinity, the number of circles, then smaller is going to be the rectangular chip or rectangular segment, so smaller is going to be its diagonal length, so it is going to approach to 0. Okay, so that's what the concept is. So what we have to do, if we try to calculate the area of this curved sector, okay, or curved strip, and we just maintain a formula of the area of the sector, which is equals to half r squared theta. And once when we are having n tending to infinity, then we are going to have definitely n number of such kind of curved subrectangular strips. So once when we sum up all those areas, then we are going to have the area of this plane G. Okay, it is a polar plane. So in that way, once when we are going to have infinite number of such rectangular rectangular curved strips, we sum up all those areas, and those areas are going to interpret the area of this region G. It's like that. So now we are what we have to do, we have to find out the area of this single red curved subrectangular strip. What we have to do, let us consider it as the area of the sector. Let it be a sector. So we know that the area of a sector is represented by this formula, r squared theta. Okay, and let us assume that this thing is like, that's an understood thing, and this thing is quite smaller. So the area of this this portion, this red portion, is represented by del A. Okay, and as it is the ith strip, so we call it del I. Okay, and it is equal to what? Equals to half del I square into del I. So how we are getting del I and all that? So actually we see that we have to find out here this angle. Okay, so this angle is representing the area of this segment, the angle of this sector. So how we are going to obtain, once when we subtract this big angle, this small angle from this big angle, and we are going to have the area of this sector, the angle of this sector. So we just write down here angle of this sector as theta I minus 1 minus theta I. Okay, and as far as the radius of this strip is concerned, you see that this red portion is lying between these two curves and or these two circles. So this circle, if I just call it as my Ri, and I call this circle having radius Ri minus 1, and this is your Ri. Sorry for that. So it's like that. Okay, so when we just subtract the area of this circle with the area of this big circle, and we are getting the area of this strip, this entire strip, which is bounded between this circle having radius Ri minus 1 and this circle having radius Ri. So we are going to have the area bounded by these two curves, these two circles. Okay, so we are going to represent the area of this portion having this radius, which is obtained by okay, that's how it is obtained. That's how this radius is obtained, and this is the angle of the sector. Alright, so I hope it is clear to you from here. Now we are going to apply here nothing but the formula, just a major algebraic identity, a square minus b square formula. We are going to open up this factor by means of a square minus b square. So it is going to be like that, a plus b into a minus b into this thing, and let it be del I, we just call it del theta, and we just segregate it, and we just specify it keeping I at the subscript, because this is the ith curved subrectangular strip, this one. So having the area del I, so once it is represented by del AI, so the corresponding angle of this sector is represented by del theta I. It's like that. Now when you just try to divide the sum of these two radii by 2, you're going to get some average radius, and that's what we are going to represent by our del I having some bar representing average radius. And why I'm writing this thing again and again, how about if I just write this difference of radii as my del Ri? That's much better way of writing. So that's how your area of this red portion is determined. Okay, so if you're having infinite number of such curved rectangular strips, and you sum up all those areas, you're getting the area bounded by these two blue rays and these two green arcs. That is the plane G. So area of plane G is obtained by taking the summation. I is going from 1 to n, all these areas. Okay, just like that. And when your n tends to infinity, then the diagonal length of the rectangular strips will approach to 0. Once when you apply this limit over here, this summation, like this, then this summation is going to be replaced by this elongated s. This r, I bar, is going to be represented by simple r. Del Ri's will be represented by the differential of your r, and del theta is going to be represented by differential of your theta. So you can observe here that in the Cartesian coordinate system, our area was represented by del xi into del yi. If you remember, you can also see the link of the subjective video in the description box below. You can watch that video exhaustively. So this thing was representing our area, and in case of polar coordinates, this combination is representing area. Okay, so that's it. So that's how you determine the area of your G. All right, and you can notice here that at this place the integrand is 1. If you just forget about this, this is the area. And if you're having simply area over here and you perform is you're simply having this combination and the integrand is 1 here, then the integral is going to give you simply the area of this plane G. And if we just introduce here a function which is continuous throughout the plane G, this function, and it is also here, then you perform integral. It is going to represent the volume of the object bounded by this plane G and the surface which is going to be right above to it. Okay, the interpretation is just exactly how we understood in the previous video when we were discussing the Cartesian coordinate system. So the entire stuff is same. The only difference is the representation of the coordinates, and that's it. So this is exactly how we just, these are the coordinates, and this is the combination how that we apply in the double integral while using polar coordinates. Okay, so this is it. Now once when you perform the, and one thing more, I just forgot to write double integral in the flow. So this is it, because there are two summations obviously. So once when you perform iterated integrations, and let me apply here the limits as well. So here my radius going from r is equals to a, r is equals to b, and here this theta is going from alpha, theta is going from beta. These are actually the limits of your theta and your r. So in case of performing iterated integration, you can keep your theta constant and you can express your r as a function with respect to theta, and also you can integrate by keeping your r constant, having numerical values, and you express your theta as the function with respect to r. So you can do the iterated in double integration through both ways. So now let's move ahead to the example. Okay, so here you go, the example. Over here they have said that we have to find out the area that lies inside the cardioid, having this equation, and outside the circle, having this radius. Okay, this equation clearly explains that we are having a circle having center at the origin, and the radius is equals to a, and a is any number, any real number. It's like that. Okay, so here a is not actually specified. So first of all, what we have to do, we have to find out the region G, whose area we have to find out, and this G is going to be bounded by these two curves. It is, G is bounded inside the cardioid and outside the circle. We have to be very cautious in this specification. Okay, so first of all we have to sketch the figure. With that respect, we would be able to find out the limits of our theta and r, and then we are going to apply the double integral. So first of all we are going to sketch the cardioid, and we try to understand its symmetry with respect to pole and with respect to the initial line and all that. Because it's too easy for us to sketch a circle, it's not a headache for us, but the major point or the major task that we have to perform here with due concentration is the sketching of the cardioid. So first of all what we do, this is the solution, and we have to check its symmetry about the initial line. First of all we are talking about the cardioid, so how we check the symmetry about the initial line? So if your equation of the cardioid, if it remains unchanged when r theta is replaced by your r and minus theta, then we are going to say that the figure or the curve is symmetrical about the initial line. So if I just try to manage here, that if my r is r here and my theta is replaced by negative theta, we know that cosine is an even function. So if you enter here a negative angle it is anyhow giving you a positive sign, a positive answer. So in other words, you can say that it is something like this. That's the definition of your even function, that if you put a negative independent variable, it is going to give you same function back. There's no change in signs. So same process is happening here. So cos of negative theta is equals to cos theta. So you see it is restored. So if your r theta is replaced by r minus theta, the function is unchanged. So it means that the cardioid is symmetrical about its initial line. All right. Now we are going to check its symmetry with respect to the pole. So how we check it? That if your function, or the given equation, if it changes when r theta is replaced by either negative r theta or by r and pi plus theta, then we are going to say that if it changes, then we say that it is not symmetrical about the pole. And if it remain unchanged, even if we replace our r theta by either this or by this, then we say that it is symmetrical about the pole. So let us try to check and see if it is maintaining its form or not. So if I just replace my r and theta by my negative r and theta, so it is, you can see that negative r is equals to a 1 plus cos theta. So this shows that r is equals to negative a, or in other words, r is equals to negative a 1 plus cos theta. So now there is a change with the sign. So you see the function is not preserved, it is changed. And either if you just replace your r theta by either by r or pi plus theta, you just substitute pi plus theta over here, then in that respect as well, the function is going to be changed. It's not going to remain same. So you can use here the formula of your cos alpha plus beta. So if you just replace your theta by pi plus theta, okay, and you just apply here this formula, this cos alpha, that's a preliminary formula here. So I've just tried to put down my pi and theta at the place of alpha and beta. I substitute over here in the formula. So cos pi is negative 1, so it gives you simply negative cos theta, and this thing is 0, so this entire stuff becomes 0, so I'm not writing it here. So you see cos pi plus theta is equals to negative cos theta. I'm going to write right at this place. So this thing shows that r is equals to a 1, and this becomes negative cos theta. So you see the function is changed. It is not same. So this thing shows that your cardioid is not going to be symmetrical about the pole. It is not symmetrical. Now the third thing that we see is the position of the pole relative to the curve. So how we determine the position of the pole relative to the curve? We just put the theta equals to 0 in our given equation, this one, and in that respect we will try to understand the position of pole with respect to the curve. So if you just put your theta equals to 0 in this equation, then what is going to be the value of your r? That's what it is all about. So cos 0 give you 1, so it will give you a 1 plus 1, so it is equals to 2a. Okay, so if your theta is 0, then r is equals to 2a. That's what this point is about, and we just did that. Now the fourth thing is that we have to find the table of values. Okay, so after that we would be able to sketch the cardioid. So over here I just tried to manage the table of values. I selected couple of angles between 0, including 0 and 180 degrees, and I just picked up these angles here. And when I substitute these angles one by one in my equation, this, I will get my value of r. So it's a common maths, everyone can do it. So that's why I don't think that I should mention the working here. So I simply wrote the values directly of your r. So it is over here. Okay, you simply put the value of your theta right at this place, and you just get the value of r. So it is right over here. Now what we do now, over here the axis is drawn, and now we have to sketch. First of all, we are going to draw these angles. Okay, from 0 to 180 we have to draw all these angles right here. So in the first and the second quadrant the angles are going to be, so let us try to draw this thing. Okay, that's how I sketched here these couple of angles. Okay, you can see it's labeled over here as well. So that's it. Now as far as these values are concerned, the radial magnitudes, how we are going to plot it, because we do not know the value of a, so we just assume that let a is equals to 1 just for the sake of plotting. Okay, now we have to assign the scale here. So this is my scale. Now it's my choice how I select here that is suitable with respect to my with respect to my length of the page. So you see 2 centimeter I've just taken equals to 1a. Okay, so this is it. I just took 2 centimeter equals to a, and this thing shows that 4 centimeter gives you 2a. Now if I multiply both sides by my 1.86, then I come to know that my 1.86 will be equals to 3.72 centimeters. So I just truncated 3.7 and I measure it from here, and it is coming at this point. So in this way I'm going to maintain all these r values on their corresponding angle rays. Okay, so that's how it looks like. These are the points that I have just tried to plot on the basis of this scale. So it is 0.6 centimeter, this is 0 centimeter. So I've just managed this scale, okay, and I just maintain these points, and then I'm going to join it. I will join all these points from here to here like this. So I will get just half of the cardioid, and then I'm going to draw the symmetrical portion, the remaining portion, right symmetrical with respect to the initial line. It will come over here. Okay, so that's how the points are joined. Now I'm going to draw its symmetrical portion with respect to the initial line right like this. Okay, so that's how the cardioid looks like. Okay, so now the next thing, we have to draw here a circle having center at the origin and having radius equals to a. So here you go. This is the circle having radius r equals to a. Our G actually lies outside the circle, and it is inside the cardioid, and my pencil is stuck. Okay, now I got succeeded. So the region G is lying outside the circle and inside the cardioid. So this entire portion, all this thing, this whole thing is the required region whose area we have to find out. Okay, so that's how it looks like. So now the objective is what could be the limit of our theta and of our r. So you can see here that the region is starting from this point and ending at this point. Okay, starting from this point, ending at this point. So this thing shows that theta is, the upper limit of the theta is going to be the positive 90 and the negative 90. Okay, you know that anti-clockwise angle is positive and the clockwise is negative. So the theta, actually the limits of the theta are going to be this. Okay, and as far as the limits of r are concerned, you can see that the radius is varying from this point to this point. Okay, so the value of the lower limit of the r is going to be this, starting from this and ending over here, and this point is representing this curve. The equation of this curve is this. Okay, so the upper limit of the r is this curve and the lower limit of the r is this curve. So r is equals to a and r is equals to this. So this is the limit of your r, and is expressed with respect to the by means of a function having theta as the independent variable. Okay, so here you see the theta is constant value, where if fixed, it is having number values, and r is expressed in terms of theta. Okay, so actually the integral will appear something like this. The required area is going to be, integral is going from negative pi by 2 to positive pi by 2, and a is going from a to a1 plus cos theta. Okay, and r dr d theta. That's it. So that's how we are going to perform the integration now. Okay, so I've just maintained the entire calculation already, so I simply just orally I will dictate this thing. So the integrand is, we are going to integrate with respect to our r first. Okay, that's what we are doing. So r integral is going to give you this. You apply the limits, it gives you this. You just take out your a square outside of the constant, and it's coming common actually, so that's how you get. Now you open up this 1 plus cos theta with respect to a plus b whole square formula, and you just got this thing. This minus 1 is copied as it is. Then you individually going to integrate. You can see that plus 1 and minus 1 is cancelled. Only these two things are left to be integrated, and it will be done soon. So you see, we are going to open up this cos squared theta by means of this formula like this, and then we are going to integrate this term, this term, and this term, because these two are already cancelled. Okay, so now we just apply the limits, we just apply the integral separately like this, and we just directly do that. You know that the integral of your cos theta is sine theta. You apply the limit. Integral of your one integrand with respect to theta give you theta. You apply the limit, and then the integral of your cos 2 theta gives you this, and you apply the limit. So once finally you just put down your upper limit and lower limit one by one. You take the difference. You got this. You simplify entirely, and you just got the answer of your area of this region. Okay, right over here. Alright, so that's all for today, and I hope this video was have taken too much time indeed. But if you got the chance to watch this video to the whole length, and I'm sure it is going to help you out in getting the concept.